All right. Welcome back to the second to last day. Quick announcement for today. We changed the agenda slightly. So we'll be having a session now with Nils Lukas, and then we'll have group work, then we'll do lunch, and then we'll do Louis Secco session. So the agenda online says that we'll do Louis Secco at 11:30, but we'll do group work first, then lunch, then Louis Secco in the afternoon, and then another round of group work. So session, group work, session, group work. All right, so let's start with our first presenter for the day. It's a great pleasure to welcome Nils Lukas from MBZUAI, or MBZUAI. For those of you who are not familiar with Abu Dhabi and the ecosystem, it's one of the universities in Abu Dhabi, and it's, I think, one of the only or the first university worldwide that is purely focused on AI and data science. It's a really strong university in Abu Dhabi. I've got a couple of really good researchers there, strong students graduating from there. They also do Ph.D. programs. And Nils is originally from Germany, which is a great pleasure for me, so we can talk German. And he changed his topic slightly. He's an expert in trustworthy and AI and safe AI. And today he said he will talk about alignment, oversight, and deception of safety in AI. So looking forward to your session, and the stage is yours.
Yes, thank you very much. I hope everyone can hear me, and thank you for having me. So I want to talk about a topic that I think most of you don't know about. And this is, I think, an emerging topic. It's in AI safety. I was a bit unsure on what your background is, so I'll try to keep a lot of the high-level ideas very understandable, but also there's going to be times when you might have to stop me and you might have to ask a question. Okay, and if that's the case, just raise your hand, or let's see, I mean, if it works, maybe you can start just by speaking out, right? Or actually, no, let's say raise your hand and then ask a question immediately. It's better to clear that out right away, okay? Okay, very nice. So my first question to you is, who knows about alignment, oversight, and deception? Just as a raise of hands, who would feel comfortable in explaining potentially what that is? Let's say maybe just alignment, right? You've all heard probably of alignment. I'm not going to ask you to explain it, but just as a show of hands, who knows what that is? Okay, so like 30% of the room. Okay, oversight is then a topic that probably a lot of you don't know about, and deception is something that I'm barely going to talk about today, but it's maybe one of the most pressing problems we have in AI safety today. And of course, if I have deception in the title, I have to deceive also on the slide a little bit. So someone already pointed out that there's a camel here. So this is in Abu Dhabi in front of the Grand Mosque. And typically in commercial previews, you would see camels running through Abu Dhabi, or being close to Abu Dhabi. And that, of course, isn't the case. It is AI generated this camel. And it should illustrate the point to some sense that it's quite easy to deceive people of things that are plausible. Okay? And if you don't have the full picture, it's very difficult for you to verify if this particular piece of information is genuine or not. And so what that means and how we can ensure, let's say, truthfulness and honesty, that's what I want to talk about today. So a little bit about myself. So I'm from Germany, I went to Canada, and I'm at MBZUAI since August of 24, so I'm an assistant professor there. I worked with some industry partners, most recently with Etihad Airways, actually on self-improving systems in custom environments. And my research focus is largely on AI security. So security is always the study of the worst case, right? What's the worst that can happen? So you have an algorithm. Probably all of you have a computer science background, right? Like what's the complexity, right? In very general terms. And what we care about in security is always the worst case outcome or runtime of an algorithm, right? And typically in machine learning, you study the average case, right? I want a model that on average gives me the right response. But in security, we want a model that in the worst case still gives me a response I can work with, or at least one that doesn't do harm. I also now recently do some stuff on interpretability. Privacy preserving machine learning is a really exciting topic. I know it has the word privacy in it, which maybe turns some people off, but it's very, very interesting because fundamentally it's the study of information and information flows, right? And then finally, I also do some stuff on applied cryptography, homomorphic encryption, and that sort of stuff, but I'm not really going to talk about that today. So let me kind of zoom back 12 years in time. So 2014. Who knows about adversarial examples? Who's heard of that before? Maybe also as a show of hands. Okay, that's good. Most people have heard about it. So what it is in 2012 approximately, we had image classifiers. In 2014, we found that we can manipulate the input just so slightly by adding some random noise pattern, so that if we overlay this random noise pattern with the input, we see that the prediction of the machine learning model is changed. So the model is deceived. And of course, that's a big problem because a human would still say that nothing changed, but the machine learning model wouldn't do that. So there's some sort of holes in generalization that is very difficult to actually get rid of and quite easy for an adversary to exploit. And it turns out that this wasn't just limited to these small image classification systems, but it even extends to superhuman AI. So superhuman in the sense that they play Go. So Go is an old Chinese game. They typically say it's a bit more complicated to solve than chess. And they also measure performance in ELO, which basically quantifies how likely you are to win against another opponent. So 100 ELO difference, I believe, means that you will win approximately 70% or so of the games, right? And it exponentially decays, so you will never win against someone with 500 higher ELO. That just won't happen. It's not very likely. And so what we managed to do is we got training algorithms to train superhuman systems. So systems that wouldn't learn just from human supervision, but that would find their own strategies and exceed them in capability. However, towards this adversarial policy, what you can do now is you can freeze the system, right? So you don't update it any further. And now what you do is you train an opponent from scratch against that system. And that opponent, you train and train in the same way that you trained originally the superhuman system, and you're just trying to find winning strategies. And what it turns out is that in just 0.1% of the compute, you can find adversarial strategies, some of which are even human playable. So they found strategies that you can explain to a human. That human goes up against this player, and every time you're playing this strategy, the human will win. So that's, of course, surprising because we say it's a superhuman AI, but it's absolutely not secure in the sense that it has these gaps in performance, right? And yes.
Regarding this strategy,
yes.
Is this strategy something that already exists for humans, or it was like a completely new strategy?
No. It was a completely new strategy that they found via this optimization procedure.
Okay.
Right? I think even it's in the image. Like in the paper they describe it. No, it's not in the image. But in the paper they describe it very well. You build like a weird looking wall around your opponent. It's very interesting.
So it's also something like a human would not come up with.
No. Exactly. Yes, because there's so many like strategies and possibilities. It's very unlikely, yes. So that was, by the way, in 2022, so quite some time ago. And we all, I think, adopted AI at some level now. And so I have to introduce this concept of AI agency. So AI can be a tool, it can be a consultant, it can be a collaborator, an expert, or running fully autonomously. And really how you use AI and what kind of agency you give AI determines what kind of harm, let's say, it can do and what the action space of the AI is. So for example, early on we used maybe Claude or Claude Code as a tool in, it writes us a draft for an email. And now we're using it more as an expert, or at least I have, right? Where I ask for literature review, give me some opinions, I don't understand this, explain it to me, right? Also computer use agents, of course, where we do some sort of, let's say, coding tasks, or maybe setting up a Linux server, right? I have no idea how to do that, but I know what I want. Okay. So how many of you, maybe also again with a show of hands, I know it's not too much, but how many of you are using coding agents at least once per workday? At least once per workday. Okay, that's about 60%, I would say. Oh yeah, by coding agents, by the way, that's what I mean. And that's, sorry, that's not too surprising because Anthropic recently published how these agents are being used and by whom. And a lot of them, I think 50% of the domains where it's being deployed currently is software engineering, which I presume a lot of you use these tools for. Okay, So then we have to get one more terminology out of the way, which is this distinction between AI security and AI safety. So typically we say, or for the remainder of this talk, I'm going to assume that AI safety is the essentially problem of mitigating unintended harm. So there is something, let's say we have a car, right? I want to operate my car, but I might crash it against the wall, right? It would not be safe if it didn't have an airbag. I didn't intend to cause harm, but we designed the system so that even in that case that might just naturally occur, there is still some safety mechanism. Okay, so there's really no adversary. There's some sort of natural environment that we sample from, and that natural environment gives us these events that cause great harm. And that's what we want to mitigate here. And that is opposed to the AI security definition, where we care about intended harm. So what we do is we define an adversary. And if we take that same analogy from this like natural environment that we sample from, right, here the adversary will not sample randomly, but they will always pick the worst case outcome. Okay, they always play it back. If there's one worst case event, they will do that. So if we go to this car example, for example, it's somebody breaking into your car, right? Like there might be 1,000 ways to do it. They will choose the easiest one. So, and that's the one that you would essentially have to protect against. Okay. So there's of course some sort of overlap between those two, and the overlap we call a part of trustworthy AI, right? So trustworthy AI can, like, definitions vary here, but for my talk I'm going to use that definition, is we have some sort of AI safety, we have AI security, you can see different problems and questions, and sometimes these two might come together. So for example, if the model itself like is scheming or is decepting against you. Why that would happen, I will talk about in a few slides. Okay, so this is the analogy that I also put into a slide because I'll share the slides with you later, and I didn't want you to just have to depend on my words. It's essentially that analogy that safety enables security. So if you, let's say, have a car and you build the car out of strong materials that would maybe prevent a collision or survive a collision, it is also probably robust against attacks. Somebody smashes your car or something like that. Okay. So I'll quote Eric Schmidt here in 2024. Eric Schmidt was the former Google CEO. And on the question of AI safety and how to deal with it, he said, how do you detect danger in a system which has learned it, but you don't know what to ask, right? It's learned something bad, but it can't tell you what it learned, and you don't know what to ask. So the system that we're building here in AI is so complex, and it might do so many things that it's very difficult to just enumerate all the capabilities and write unit tests for those. There's this problem of like unforeseen capabilities that the model might have learned. And that also brings us to the alignment question, which is the study of, or which is finding methods in order to make the model do what I intended to do. Now that's sort of more a philosophical definition, because of course, what is it that I intend the model to do? It's very hard to specify that in a rigorous way, right? If I could specify it in a rigorous way, it wouldn't be very hard for the model to follow it. But let's say I want the model to cause no harm, right? There's so many ways in which it could cause harm. It's very difficult for me to enumerate them all. So I have to rely on the model being a reasonable interpreter of my specification, of my request, just I would expect a human to follow my specification and reasonably interpret it at runtime, so to speak. Okay, and so this is the graph of like progress in AI in 2023. There's a more recent one, which I'll show also in a little bit. But at the time in 2023, people were plotting the performance on a lot of the, let's say, now we would say, simple tasks like ImageNet, MNIST, the GLUE dataset, GPQA, and so forth. And you can see that there's a quite strong improvement in capability. And just to give you a little bit, before I get to the alignment, oversight, and deception, to give you like a little idea of trustworthy AI and what it really means is, and also we have a course on this, so this is a course slide that I took from our course, is there's a lot of topics in security. For example, where you look at collusion or agentic security or adversarial robustness that you'd like to study. Then you have privacy and fairness, which is, for example, a framework called differential privacy, even federated learning or inference time privacy. There's the governance and economics part, where you care about how is the model being used and what kind of economic impact might it have. Then you have attribution, which is, let's say, grounding, right? Can you explain, can you show me where your information came from? Can I trust you? Then there's reliability, which typically in how I would specify it is evaluation, but also formal ways to guarantee robustness. So I would like to guarantee for certain inputs that there is no, let's say, security exploit against these types of inputs. And finally, there's the safety question, which we'll focus on today a lot, which has like capability forecasting, misuse, recursive self-improvement, and so forth. And just to illustrate to you that some of these problems are really hard, can someone tell me what sort of information might be hiding in this image? Okay, maybe I help you by changing the perspective a little bit. Okay, it's very difficult to spot when information is leaking, and we don't know how to really, do that and how to make sure that information at training or inference time isn't being sent to an adversary. And also, like more classically, I focus, of course, on security threat modeling. So there's various types of threat models that you may or may not have heard about, but if you go into AI security, this is the first thing really that you learn. And one thing that we already know for existing complex systems, but especially which becomes important for AI, is this idea of the Swiss cheese model of defenses. So instead of deploying just one defense, right, that might or might not be vulnerable to certain exploits, you want to layer them and stack them and put them all together. And this is also some, let's say, recurring theme that we see in machine learning. Let's say security and safety is that typically you have different types of ideas and you try to put them together and see, okay, does that work fairly well? And in academic research, we typically focus on one security mechanism at a time, and we can see, okay, look, we can exploit that, we can do this and that. But in a realistic environment where you have uncertainty, multiple defenses, and so forth, it becomes much more difficult to actually exploit these systems. Okay. Now we get, sorry. Now we get a bit closer to the main topic of this talk. So I want to introduce to you what I call the AI safety stack. Okay? So the AI safety stack here has 7 components. It goes from training to specification to oversight to robustness to deception to interpretability and control. Now, how many of you can explain to me what I mean by specification already? Like, what does it mean to, let's say, specify some desired behavior? Who knows here what's a constitution? Has anybody heard of that term? Can you show clear hands? Okay, 1. So I like it because that kind of validates my initial hypothesis that this is a quite understudied topic that most of you probably don't know about yet. But it's really of fundamental importance, I would say. And also it's a very emerging topic. So if you're just starting off doing a PhD or maybe you're thinking about a master's thesis that you're writing, consider these topics as well. And there will be plenty of references to papers that you can look into. Okay, so in my talk, I cannot talk about everything, unfortunately. I really would like to. But I want to give a detailed, close-up look into the first 3. So the training, specification, and the oversight part, which essentially allow you to train a model and control its behavior and have some assurance that however you trained the model follows your intended specification. Okay, that's what it is. So you start off before training with nothing, let's say a data set, right? And after the oversight part, you know that your model will follow your behavior under certain assumptions, will follow your specified behavior. I want it to be an AI trading agent that makes a lot of money and don't invest into these kind of stocks in a very simplistic scenario. And we know that the model will follow this accurately. Okay, we have formal guarantees for that. But of course the problem isn't solved of like getting usable AI or AI that you can deploy in the real world, because what we don't consider here are adversarial attacks, right? Where you have someone who's trying to then manipulate your system by feeding it wrong data or by deploying an adversarial attack. Also, what we don't cover is scheming and deception. So I put it in the talk title, but I'll talk about it in future work, where essentially, while training the model itself might have some sort of agenda or awareness that it's being trained. So it's trying to manipulate your training process to achieve a certain outcome that might appear to you as if it's aligned, but it's not really aligned. Now, to the best of my knowledge, these scheming models require quite a lot of capability, and from my point of view, today we don't have scheming models. The models that we're training, I don't believe that they're yet scheming. So it's really kind of an emerging topic, and early research on this is coming out, mostly by Anthropic and others, but I would say the judge on that one's still out. But this is certainly kind of a risk that might occur in the near future. Then we have interpretability, where we'd like to understand the model, and we'd like to not just understand it for the purpose of like vacuous understanding, but we'd like to understand it in some capacity that we can control it, right? Ideally, what interpretability, I think a lot of interpretability is being used for today, is that we have some training mechanisms and we can train the model to do certain things, and maybe the model appears to do these things very well. But with interpretability, what we can do is we have a second way to verify that this model is behaving the way that we intended to behave. Right? So if you look at the activations, right, maybe you decode them to natural language, what is the model doing? And you can use that as a method of control. You can tell whether or not the stack that came before has failed or not. But interpretability you typically don't want to include during training, because if you include something during training, you allow the model to adapt to it and adjust its responses. So you don't want to do that. But interpretability, it's quite crowded, but it's also a very interesting topic to check whether or not everything that came before actually worked. And then finally, we have control and security. So these are, I would say, what I focus on more classically. I would say these are systems with provable or formal security guarantees. So here, typically, the assumption is that we have a machine learning model, like let's say an LLM, we deploy it in some environment, let's say on my computer. And now we assume the model will fail on every interaction that we provide to it. And we try to design a harness or a system, a control system around it that will mitigate these types of failures. So papers, for example, here would be the CAMEL paper by Google DeepMind. And there's a lot of research going on in that. But I won't talk about any of that second part. Okay, so I wanted to make this a bit interactive. So one of the last questions that I have is, by the end of 2027, how capable do you believe frontier AI agents will become? So there's 4 options. So maybe most short technical tasks, like writing functions, simple bugs, will be AI will be used for. Many full workdays of technical work, so you can run these AI systems for a very long time to solve rather complex problems. Then significant parts of AI research and development workflows, or the entire research program in narrow domains will be automated. So can I maybe ask who thinks that it's going to be A? And of course, these are like, subsets of each other. So, okay, by just a show of hands, who thinks it will be A? Okay, nobody. Who thinks it will be B? Okay, like 4 people. Okay, who thinks it will be C? Okay, that's the vast majority of people. Okay, that's, I would say, like 70%. And then who thinks it's D, like entire automation? Okay, 1 person, very nice. Okay, hopefully not. Yes, so for those of you who don't know, it was a very influential or well-cited report on AI 2027, where they essentially made a website to kind of try to predict these events and what will happen by 2027. And the story, like I think it was made in 2025, early 2025, I think they're already quite off track, right? Like we do see strong capability improvements, but here they talk a lot about, let's say, governments interfering and stealing model weights, and at least we haven't seen that so far. But one thing that I want to point to is this curve here that they are predicting, where they assume that you have some sort of self-improving system after some time. So a system that that doesn't need a human supervisor anymore to create its data, or maybe it only needs that in a very limited capacity, and it can check its own work and improve in these systems. And maybe you've also seen these meter graphs. right? Where on the y-axis you have the amount of time that it would take for a human to solve a given task. And on the x-axis you have the release date of the model. And the y-axis is logarithmic, so this would be exponential, right? But I think this graph can also be misinterpreted. So this graph suggests that you have this exponential trajectory, right? But also it can be a bit misleading, because what tasks are you talking about? And a colleague said to me recently that a calculator, right, would also have kind of an exponential trajectory here, right? Because for a human it's very difficult to actually multiply numbers. It takes you a lot of time, and if I give you bigger numbers, it's going to take you more time. So also a calculator would, maybe show an exponential takeoff, but we're not afraid of that. So the question is, of course, how will these capabilities develop in the future? Okay, now let's get a bit more technical. I think I've given some introduction now. Let's start with I want to zoom in on these 3 parts of the AI safety stack. So first, who knows how the pre-training, SFT, and RLHF part works? Did you already have that in a session that I didn't attend? Did anybody talk about the specifics, how that stack works? Okay, I take that as a no. Okay. So this is a very nice picture that I like a lot because it evokes kind of emotions. So essentially you have 3 parts. So one part is pre-training or unsupervised learning, where what you do is you take you take a data set and you train the model to only predict the next token. Right? That's all you do. It's sort of a compression task. And you use the cross-entropy loss for that. The next part is supervised fine-tuning. So here you have typically not just any data, but you have human-curated data that comes in a paired format. So you have an instruction and you have some response of the model, right? So what we want to teach the model there is to follow instructions. And again, we use the cross-entropy loss to do that. It's basically the same task, but the data is much more expensive because we can't just take any data, right? And it teaches the model to follow these instructions. And finally, this very little part at the very end is typically what we refer to as alignment. So here what we're trying to do is we're trying to give the model rewards. So we have a different training strategy where instead of supervising the model, right, we show the model what it's supposed to be doing, we only specify to the model what is good and what is bad. Because we cannot really know that ahead of time for all of the possible answers. So we have to typically train a model for this or employ a human to actually provide this type of feedback. And Boaz Barak, Professor Barak, has a very good lecture slide on this, which I took. So pre-training is exactly that you have this document, right? SFT is you have a prompt and a response. Those two are typically considered off-policy optimization methods. They're off-policy because the demonstration came from a different teacher, not the model itself. Okay? Contrary, in reinforcement learning, for example, via RLHF or RLVF, right, which is reinforcement learning with verifiable rewards, you have the model producing a response and some judge or evaluator or verifier telling you if this should be a good response or a bad response. Okay? So what we do in RLHF typically is that we take a lot of human feedback to some answer, to some questions, and we rate some answers as good or bad. Now the problem is human feedback doesn't scale very well, so we'd like to train a model to learn how we would assign good or bad labels. Okay? And then we can deploy that model and somebody can just train against that model. Okay? That's typically what we call a reward model that we're training. And really the reason why supervised or supervision alone doesn't work is because in supervision you don't know what the model really learned, right? If you visualize the output of a model as some sort of state space, then in supervised learning you can increase the probability of visiting certain states, but you cannot decrease the probability of visiting others, maybe unwanted states. And with reinforcement learning, we can give some optimization pressure to decrease the probability of visiting nodes that we don't want you to visit. Okay, so this is also sometimes like called some sort of contrastive learning where you would like to shape the distribution of your student model. Okay, so sometimes we're very lucky and we have verifiable rewards. For example, if we play a game of chess, right? We all know we don't know what's the best move, really, right? Like if I give you a chessboard and I ask you what's the best move, you don't know. But if we play the game out until the very end, we have a deterministic verification function that can tell us who won. And then it's all a credit assignment problem, where the model has to figure out, okay, why did I win? Is it because of this move or that move? And really this credit assignment problem appears a lot in every task, not just chess, because every token can be seen as some sort of move the model is making. And the model continuously has to figure out which token is the most important one. And and with verifiable rewards, we can do reinforcement learning quite effectively, where if you throw a lot of compute at it, right, you at some point the model will figure out exactly what actions to emit in order to maximize the reward. Okay, and this is this token space, let's say, right, and reinforcement learning, for each token, I assign some optimization pressure on whether or not to increase or decrease the likelihood. And again, if it comes from anybody else but the student model, we call it off policy. If it comes from the model itself, it's on policy. And you can imagine the student having some sort of probability distribution, right? And in on policy methods, you always regularize it to stay close to its original distribution, because you're just like the model already has a high probability of emitting this token sequence, and you're just pushing that probability a little bit up or down. Whereas in the off policy case, you don't have any anchoring typically to the original distribution. So the model might forget everything. That's why, for example, in supervised learning tasks, you have this problem of catastrophic forgetting, which empirically, but also there's some theoretical justification, in reinforcement learning just occurs way less, right? Especially if you do it on policy. Okay, and there's some interesting, let's say, problems of, okay, how can a model learn which tokens to emit? Because the underlying reality of that token might be very complicated to learn, right? So for example, if it's the next word in a poem, maybe it's easy because like there's so many poems that look alike. But if it's the next step in a mathematical proof or a program, it might be very difficult to model that next token because you have to model the whole reality behind it, which might be a lot of theorems and proofs and so forth. So the problem here really is, it's called Bourgain's problem and Gower's problem, which is how specific should your training data be, right? And how redundant should it be? So for example, let's say you only train on very dense mathematics. Then maybe your model never learns the underlying reality, but it only learns these spurious correlations to emit the next token sequence that looks like it fulfills the proof. Whereas in the other case, in Gower's problem, maybe if you make it too verbose, you're wasting a lot of tokens, and maybe the credit assignment problem is very difficult. So really what we want is we want some sort of adaptive compute, right? We want the model to learn how many tokens it can emit to solve a certain task, and this is typically what we call then reasoning models, right? And in reasoning models, we have some, let's say, chain of thought or some intermediary tokens that the model can emit in order to solve a given task. But really, you can think of tokens as compute, right? It's some sort of variable compute. Okay, so now what we have with this sort of pre-training. So we have three methods, right? Pre-training, supervised fine-tuning for the instruction following part, and then we have some reinforcement learning on top. So we went essentially from data to a model that follows instructions. And with reinforcement learning, for example, we can also specify some good and some bad parts. But this specification is rather rudimentary. It's very difficult to say something high level, right? Unless you want to sit in front of the computer all day to wait for good samples to come across that you can then label. So really what we would like to do is we would like to enter the second stage, where now we have a model, okay? And maybe we can just tell the model what it is that we want, how we want it to act. So traditionally in AI safety, you would give a constitution. So let's say a document with rules of what it can talk about. Like for example, in mustard gas, right? Like you can talk about mustard, but you cannot talk about mustard gas, like these types of things. But really it goes beyond safety. Safety is just like a really strongly motivating use case. In very many cases, especially today with agents, we don't have training data for them because they're deployed in some environment. Let's say, for example, for us at Etihad, we have a collaboration, right? They have, let's say, an environment with 150 tools where they would like to deploy their agent, but they have no training data because the environment doesn't exist. They created it specifically for that agent. Now there's two options. Option one is a human goes and just teaches the agent by instruction pairs, but that will take an incredibly long time. And anytime the environment changes, you have to redo the whole process again. So that's terrible, right? A much better way, and that's the way that the second way goes, is, okay, let's leverage the model that we've just trained, which can do some sort of instruction following, to try and specify what kind of training data it should generate for itself. Okay? Then what we do is we just ask the model, okay, here, sit in this environment, try things out. I'll give you a few queries, and you have to produce answers. And then I can tell you which answer is good or not, or you can tell yourself based on the specification. So Anthropic, for example, is doing that. They do constitutional AI, what it's called, where they have a very long document that exactly controls what the model should do and should not do. And then they give it to the model, and they have this special way, which I'll explain in a second, so that the model learns itself to follow that constitution. Okay, so it creates its own training data, it trains by itself, and in the end you have a model that follows that specification. So instead of having to specify the data, you just have to specify the behavior. That's the second part of this AI safety stack. Okay, so let's go a little bit into AI constitutions. So what's a constitution? A constitution is a set of rules, and we had rules like this for robots, for example, for a long time, even though probably they're not sufficient in practice. Now we have much longer rules, but this idea has been around for a much longer time. And if you look at, for example, OpenAI and current model providers, they have what's called the model specification card. So you can browse it actually. It is I think, like 30-page document, something like that, where exactly it tells the model what to do, what not to do, when something is ethical, when it isn't. And also it has some sort of role model, right? Like where does information come from? It's actually quite sophisticated and something most people don't know about. But if you get into this type of research, you should really look at these types of specifications. Okay, and so a little bit more in depth. So for example here, if the users ask, so these are all the high-level rules, and if you click on them, they will uncollapse, and then you'll see a much broader specification. And these specifications are really like programs, only that they're not formal and they're not easily verifiable, right? Okay, so for example, here for legal insider trading, there's two examples of what is okay, what is not okay. Like you can ask about it, but you cannot engage in it, right? These kind of things. Okay. And the alignment signals that we have during post-training, I've put them here. There are essentially 6 different types of alignment signals. So one can be human preferences. So this is good, this is bad. The second one can be demonstrations. Okay, here's the input, here's the question, here's the answer. The next one, as I already said, can be verifiable rewards, like in this chess game, where we can exactly tell, okay, you've done it correctly. Then we have what's called process supervision, where you want to reward intermediary steps of the model. So typically today, we don't really use them that much, but this is an active area of research in trying to train these models. Then we have what we'll talk about today, model-generated oversight. So that is debate, something that's called amplification. It's a very important word. Self-distillation, on-policy distillation, these kind of things. And finally, we have also the safety layers. So that can be some sort of adversarial process where you try to break the system or red team the system, find edge cases to then update the system, like how it interprets the constitution or whatever the specification, let's say. Okay. And let's dive a little bit into constitutional AI. So let's assume we have this constitution, which is a set of principles. Then now what we'd like to do is we'd like the model to essentially generate its own training data in order to update itself so that it better follows the constitution. And a trick that you do here, and this is a trick for all self-improving systems, right, is that you have to create some sort of gap. Okay, what is a gap? Now a gap means I have a model. This model doesn't do what I want, but it has some capabilities like instruction following. I want a model that also has these instruction following capabilities, but on top of that also follows my specification. Okay, but how do I get that? Let's say, for example, I need to somehow make the model capable enough to create its own training data. And one way I can do this is by spending more compute. Okay, for example, I can allow the model to think as much as it wants. I can invoke the model multiple times. That's called a computational gap. That's what's used to train virtually all of the AlphaGos and the chess systems, I forgot the name. Right? All of them use a computational gap for recursive self-improvement. Okay, in constitutional AI, you use something similar, so you also increase the compute, but you use some sort of deliberation training. That's what they call it. So essentially here, what you do is you give the model time to review and rewrite its own outputs. Right? So what you do is you ask the model, here's the constitution, here's the question, answer me. Right? The model will produce some output, and then you ask the model again, here's the output that was generated, here's the constitution, does that comply? Right? Give me a review, which is essentially a computational gap. Then the model will maybe say, no, this wasn't good because of this and this and this. And then you ask the model, okay, please rewrite based on that. So now you've invoked the model 3 times. You assume that if you invoke the model 3 times, it's slightly better than if you invoke it just once. That's the computational gap. And that gap allows you to do what's called recursive self-improvement, right? Because think about this. I have a model. I amplify that model in some way, right? By creating this computational gap. I just unroll it 3 times. Then I create my data. And then I train my model, the small model, on this data. So that the next time I ask the small model, it will be a little bit better because it follows the stronger, the leader, right? It will be a little bit better, but at less compute. Right? It became a bit more efficient at generating the same response because now you don't have to unroll it 3 times. You just ask it once and hopefully it would give you the right response. Okay, so it closes that gap. But, and that's where the recursive part is, by closing the gap, because it's a system where the large system is composed of the small system, by improving the small system, you also improve the large system. So you create a new gap. Does that make sense? That's a very important idea of recursive self-improvement. I have a slide on this, but I'll give you a minute to think about this. So in constitutional AI, basically, this is a nice, yes?
I have a question. In the step 2, where the LLM again start reflecting about the constitution and the how do you make sure that it doesn't deviate from the original content? Or even if you tell them to does the original constitution, original document, and the fundamental right it matches, they might hallucinate. How do you are sure that it is aligned?
Absolutely correct, yes. So how do you ensure this? Okay, so this is called basically the amplification problem. So in amplification, I mean, the ground truth has to come from somewhere, right? So it comes from the model to interpret your constitution. The constitution in this case doesn't change, it's fixed. So one set of rules, it can be a law book even, right? Interpret this law book. Now, in step 1, the model might go wrong, right? Maybe you amplify it, it still doesn't quite get it right. But what you know is that it follows the leader. So the stronger model will be a little bit better, right, than the smaller model. So it should continuously improve and until this gap closes, right? So even if in step 1 you go wrong, right? Yes, now you've amplified something that's wrong, but it's less wrong than what you had before, right? So what you do is you amplify this potential bias, right? Because it's a fully encapsulated system. Like if there is a bias, you can't really get rid of it, but you amplify the feedback that the human would give because the human doesn't have to be involved here at all. Yeah. So it's a very and then of course there's a lot more approaches because here we're really in a closed system. We have a constitution, we have a model, we want to improve on this constitution, right? But there's like live systems, let's say, that you continuously cross-check with human interpreters. And also here you would perhaps, if that's possible, also have human interpreters in the loop or testers that maybe after the model has come out to fix like these amplification issues. But this is a fundamental issue, right, that algorithmically it's very difficult to solve because you have to get more signal in some cases to do that. But it's a very valid concern. Yeah. Okay, so constitutional AI really is just one way of doing this for frontier models. So Anthropic is using that today. They even had a challenge on trying to break this constitutional AI system where they invited, I think, like 5,000 submissions or something like this to find jailbreaks against a model that has self-improved using constitutional AI. And during the competition, nobody was able to break that system with a universal jailbreak, which is that you can elicit multiple capabilities at the same time. So people were able to break individual capabilities, but there wasn't one way to break all the capabilities, right? So these self-improving systems and methods to train them are incredibly powerful because you don't need human supervision. They scale naturally, okay? And just to go through the rest of constitutional AI, so you have two phases. One is the supervised learning phase, where you create your own deliberation data. So you just ask the model to fine-tune on also the prompts of the reviewer, right, or the outputs of the reviewer, and also of the rewriter, to have this deliberation. But it's more of an engineering detail. It doesn't matter that much. And the second one is the reinforcement learning part, where you only train on input-outputs, right, created by that stronger system. Okay. Now, there's a lot of problems in constitutional AI. So, you have a question?
Yeah, one last concern.
Yeah, sure.
It's about the part about reinforcement learning with the AI feedback, the step 5.
Mm-hmm.
And it's that most of the time I read about it, a lot of people were concerned about reward hacking.
Oh, yeah, I'll talk about that too.
The LLM, like the student learns to create started examples for the bigger LLM to check, and that started to create just gibberish and useless models. So how is this tackled in practice?
Very good question. I'll answer that later because I have a slide on that as well. Yeah, but that's a great question. And reward hacking is a big concern in these types of systems. Yes. Okay, so what we see here is that constitutional AI is some sort of, let's call it constrained recursive self-improvement method. Constrained because it really only has that signal that you initially put into it. So you have all these amplification issues and so forth. Okay, constitutional classifiers, I talked about them earlier. So Anthropic had this competition where, of course, once you have a system that follows your intent, and you can specify intent in natural language, you can also train classification systems on that are quite efficient. And Anthropic is using them today, I would say quite successfully. And just to give you an idea of what these constitutions look like, for example, it can be describing non-toxic, eco-friendly alternatives to harsh chemicals, that's fine, right? But talking about, hacking into a computer system is not fine, or any of those. And these lists can become quite long. But really, I want to stress that constitutional AI is also used, like it's here we study it for safety, right? We want the system to not do certain things and whatever, but really they're also for utility, right? Because we want to have systems, we want to automate tasks, but we don't have data for this. And with the increasing automation, companies will not create data. It's very difficult to create data. So what they need is some way of prompting the model, essentially, like telling the model, look, this is what you do, but it's like 100 pages because it's quite difficult to actually specify if you had to write it down. So how do we teach the models these 100 pages? Because if you take these 100 pages, you put them into Claude Opus today, it's not going to follow them, right? Its prompt following abilities are very limited. Empirically, maybe to 5-6 pages of text. Right? Beyond that, your reliability just goes down the drain. So that's why these systems and this need to specify is very valuable also outside of safety. And we see this as a recurring theme. Really, safety in many cases is just one agreed upon, let's say, a set of rules that we can test the model if it follows them or not. Okay, so let me return to this idea of recursive self-improvement because it's very important. So you have a system, a big system, that's composed of a small system. The big system generates your data. The small system improves on that data. Since the big system is composed of the small system, the big system improves as well. Okay, and that way you get recursive self-improvement basically forever until that gap closes, right? You improve until there is no gap between the higher compute and lower compute model on that task, which can, for example, happen if you saturate, right? Maybe there's you already trained the best possible chess player, and there is no gap. It doesn't matter if you spend 10 times the compute. You had a question? Yeah. Oh, I think there's a microphone. Yeah.
That improves all of the other models, or do they also change or the system based on the model, like, or is it one general for all of the Anthropic models?
So I don't know what they do at Anthropic internally. I wouldn't have, like, I wouldn't know. But what they do is they publish their research on how they get these systems in place in the first place, right? And they share that. And so from that we can learn. And what we see here is that what they would like to do is they would like to create an extremely capable model, something like Mythos, or something that's very, 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 very strong, with a lot of compute, so that it can then be used to generate the training data for the next generation of models. Essentially what you're doing is you always improve the system by, let's say, spending a lot of compute, have that system generate data to compress the system into something that's faster. Right now, with the same compute resources, you can create better data, and that kind of recursively goes off. That's also why this AI 2027, why they assume this kind of trajectory. But of course, it all depends on, like, how big is this gap? We don't know, right? Like, how much do you get out of spending more compute? And this is purely at inference time, right? We're not talking here about training time. That's a whole different story. There's, of course, also a lot of improvement pathways there. If you, for example, select your data, if you train on synthetic data, all that stuff. But this is not even what we're talking about here. Yeah.
Thank you.
Thanks. Yeah, of course.
This cycle actually reminds me a lot. I don't know if you're familiar with self-training, self-labeling, semi-supervised learning. It's basically very much the same idea with a different objective. Before, we used to do a lot of that because we didn't have enough training data, right? So enough label data. So we basically increased the label set by teaching itself, right? Which is very much what is underlined and in here. So I was wondering, one of the most successful things that were done in self-labeling was the idea of using different classifiers, right? Inside, different base classifiers. So I wonder if the whole cycle could be the same thing, but when you go with the step 2, the create part, instead of using your own model, you would use different models, because actually they could do that, right? Just wondering your thoughts about it.
That's a great question, and actually I do have a slide on that as well. So these are the known ways to create gaps today, right? One of them is ensembling, right? We also sometimes say, like, multi-agent critique or debate, right? Like, you can do that. Ensembling, it's similar to increasing the computational gap, but it's not exactly the same, because you also have some sort of diversity coming in from other models and so forth. So this is one of the ways to do it. And maybe there are more. We're not sure. I've collected essentially the ones that we know of, like with publications behind them. And there's a lot of publications, and if you look them up, almost all of them are late 2025, 2026. And really, this is a field that seems like it's extremely interesting to study. And it doesn't have a clear answer yet, right? What is the best gap that we can exploit here? Okay, and maybe that even depends on the task that you want to train it on. Okay, so just to go over it I hope that answered the question. Yes. Okay, so just to go over it, so there's constitutional AI. There is privileged information teacher. So here, you remember this distinction I made between on policy and off policy, right? It depends on where your supervision signal is coming from. Now, you can use an external teacher to give you rewards, okay? But the reward that it gives you typically has a very low information content. If you just ask the teacher, is this a good output or not? And it just tells you yes or no, right? Then you have 1 bit of information per response. So it's very difficult to learn complex behaviors. So what you would like to do is you would like the student to generate its own perfect response, right? Like using its own words. Because maybe if you learn from the teacher, then the student has this credit assignment problem that the teacher says, look, this is the perfect mathematical proof, this is how you should do it. But maybe a lot of these tokens, they're just style tokens. Something like, oh yes, by the way, here's the next thing. Completely unnecessary. The student would have never produced them. So now the student assigns maybe a lot of credit, erroneously, to those style tokens. So that's why learning from a teacher is very difficult, because you have forgetting problems and you have the credit assignment problem, which makes it also inefficient. And you can somewhat get around that a little bit with log props and so forth, but fundamentally this problem isn't solved. A much better approach that people found recently, it's called OSDP. It's a very recent paper, late 2025, what you do is you take the solution of the teacher model and you put it into the prefix of the student model, and then you somehow give the student model an information advantage, right? Don't forget this. Here's how to do the solution. And then you ask the student to generate the solution. And now that solution is on policy, right? It already has emitted an output that has a higher probability under its current policy. So with reinforcement learning, we can shape the distribution now in the right way that this credit assignment problem is much less noisy. Yeah, does that make sense? Okay, and then we have the verifier search gap, where essentially it's much easier to tell whether or not an output follows the specification than it is to generate something that follows the specification. Then you have multi-agent critique. So here you have typically an ensemble or many different models that give you a supervision signal. And then you have more compute and deliberation. Okay? Okay. Okay. Yeah, I think we have time. So what is the alignment problem in machine learning? Who knows about this? Maybe actually, let me ask like this. Okay, A, it's building models that do what the training objective rewards, even when humans are not directly supervising them. B is building models whose behavior continues to match what people actually want, even when the reward data or instructions are imperfect. C is building models that are transparent enough that humans can understand why they produced a given answer. Or D, building models that are harmless, honest, and helpful across a wide range of user requests. Okay, I'll give it a second. Okay, then I'll take a show of hands. I'll give it one more second. Okay, who votes for A? Okay, 1. Who votes for B? Okay, it's 5, 6. Who votes for C? Okay, it's 2. So the rest I assume is all D. Who votes for D? Okay, 5. So it's very split. Okay, so it's very unclear what do we mean by alignment. So the answer typically, right, or oops, I have an example for that also. But the answer is B. So it's not really just about these are attributes, harmless, honest, and helpful. Right? These are nice attributes to have. But really in alignment, it's about intent, the user's intent. And that might be anything. Really, it's not limited to those 3. Transparency is also great, right? And understanding why the model does something, but it's not typically what we mean by alignment, right? Alignment is some sort by construction. And then A is, building models that do what the training objective rewards, right? Well, the training objective might be misspecified. That's the problem. And I have an example for that. And B really is that matching between what's the intention and what the model is doing, okay? Even when that is imperfect, even then the model should maybe ask, right, in these cases. Okay, and there's an example from 2023. It's called hide and seek, right, from OpenAI. Essentially, you have hiders and seekers. The blue ones are hiders. The red ones are seekers. It's the seekers win if they touch the hiders. And the hiders have some environment where they can take blocks and they can, block the door. And then the seeker has a ramp that they can use to go over that wall, all that stuff, right? And you can make it quite complex. And you can see this is sort of an optimization with multiple agents that have to coordinate. Okay, now this is some sort of adversarial optimization, right? Where the hiders can take these blocks and they can lock them so that the seeker is locked out. But now also for, let's say, more complicated scenarios like multi-door blocking. And then what you do is the seeker, you also optimize them. You kind of co-optimize them or adversarially optimize them against each other. And then what the seekers will eventually find is that they can use these ramps to go and catch the hiders, right? Okay, and then they lose. And so what's interesting here is that really we're looking for strategies on what is the best thing that the seekers and the hiders can do. But there's a problem of reward hacking, which came up earlier. And reward hacking here, what you see is that the hiders are taking these, or the hider here, is taking the platform to barricade himself in. Right? There's no ramp, the ramp is locked. However, what the seeker found out is that they can use the ramp to go on the block and do some box surfing, right? Which wasn't really intended by the developers, and it can still win. And these types of issues occur all the time because it's very difficult to foresee what these strategies will find. And that's what we typically call reward hacking. So I have a second example, which is the Lego stacking example. So here the goal, and this is a bit older, that's why it's more grainy. But I want to make this a bit interactive. So there's the blue and the red Lego. The goal is to stack them on top of each other. That's what I want. I want the robot to learn to pick it up and put it on top. Okay? The way that I specify my reward function is I calculate the height of the lower edge of this Lego. Okay, the higher it is, then it's stacked, right? Then the better it is. Now, what strategy do you think the model will come up with? Right? So if that lower edge of the red cube would be very large, very high, that's perfect reward. So what do you think the model might do here in order to maximize the reward?
Throw the Lego piece.
It can throw it up, but then it might come down. Right?
Or try to put him above him, or do a kind of move in the simulation.
Yeah. So what it's doing is it's just flipping the Lego over. Right? Because that is the simplest strategy that leads you to a very high reward. Because now the lower edge of this Lego block is much higher. It's actually perfectly high, right? It's exactly on the height of this blue block. So that's the problem that we're dealing with, okay? It's not that the model is trying to be deceptive or anything like that. It's really just finding low energy solution. What I mean by that is a solution that is, let's say, rather close to its already trained policy, right? That's not very complex, that it would, let's say, find by random chance, even by trying out, that gives it high reward. Okay, good. So what we want to do is now we want to somehow define reward hacking. So reward hacking is really, again, you have this intended behavior. So it gets high reward without actually learning the intended behavior. And there's sort of words that are very close to it, like reward hacking, reward tampering, goal misgeneralization, which are all different instantiations of reward hacking. It depends on what the model is modifying in order to achieve its goal. So this isn't really surprising. For example, in reinforcement learning, you actually reinforce these types of strategies. And so here, for example, we see a different type of, let's say, reward tampering, where the agent is supposed to place the ball as close as possible, I believe, to the red ball. But what it's doing is it's blocking the camera so that the evaluator has a harder time to evaluate whether or not that ball is actually close. Okay? And so why this occurs is because typically the evaluator only sees part of the environment. Maybe they don't see everything, like in this camera example. The environment is very complex and it might be susceptible to hacking, like this box surfing, right, which we just didn't intend. The target behavior may be hard to specify, so we might just be unable to exactly say what we want. Or the proxy reward is optimized very strongly. So that is when you give the model a lot of oracle access to your reward model, which also I have a slide here. And this happens, so for example, in coding tasks, we see, and probably all of you have seen that with codecs, is that sometimes here, for example, make the fastest function, and what it's doing is it's overriding the timing function, right? Like make a function that adds these two numbers as quickly as possible on a GPU. What it's doing is it's modifying the timing function to make it 1,000 times faster. So that maximizes reward, but it's not what we intended. Similarly here, but in the interest of time, I'm not really going to go over that. Okay, and we also have sort of, let's say, like we can ask the model, for example, would you ever cheat on an evaluation? It can tell you no, but then when you ask the model to do something, you can see that it finds evidence of cheating. And if you ask the model afterwards, okay, do you think that's cheating? The model says yes. So there is some, let's say, weird behavior coming on. And for alignment, we typically have two views. So you trust a less capable model because that model is not able to find all of these difficult strategies. So it's easier to supervise because the capabilities this model has to find strategies is more limited. Whereas for a stronger model, right, it can find any strategy, but it also can follow intent and policy typically much better. So really there's this competing view of how we should do this sort of alignment, which models we can trust. Okay, I'll go a little bit quicker just in the interest of time. So we also have evidence of reward misalignment happening in very simple, let's say, training application. So really this happens whenever you train. It happens not just in reinforcement learning, but also in supervised fine-tuning. For example, with spurious correlations or shortcut learning, right? These are all ways in which the model can reward hack. Okay, so here what they did in 2022 is they had an experiment to see reward misalignment. So you have an oracle reward. That is what I truly want, right? Maybe I specify that via Claude 4.5, whatever. Then I have a human reward. These are data sets that I labeled, right? This is good, this is bad. Then I have a proxy reward. So that is the reward, that is the reward model that is trained on this human data. Now the human data is of course incomplete, and the reward model, it might be quite small. So my question now is, if I train the model, right? If I train my agent against the proxy reward model, and I track both the golden reward, right, this oracle reward, and the proxy reward, will they diverge or will they stay close to each other? Right? If they diverge, that's a problem, because then that's evidence of reward hacking. Right? Like it's not really it's not increasing the reward on my true reward model, but it's further increasing the reward on my proxy reward model. So here, what they look at are two policies. So one is best of n sampling, and the other one is just reinforcement learning. I believe it's with PPO. Oh yeah, it even says there. Okay, let me go to the graphs. So what we see on the x-axis is the KL distance between best of n policy and the initial policy. Okay, so basically this is a proxy for how long have you trained. Okay, the further these, like the base policy and the trainable policy are, typically the longer you've trained. And we measure this with the KL distance. Okay, and then on the y-axis we have the reward model score. So the higher the score of your reward model, the better it satisfies your reward model. Okay, so the better it is. Now the faint lines, okay, the ones on the top, are the gold model rewards. The solid lines are the proxy rewards. Okay? Sorry, it's the other way around actually. The faint lines are the proxy rewards, the solid lines are the gold model rewards. Okay? And what we see is a very large misalignment that occurs here with virtually all of the models. And we can see that as the proxy model size gets larger, this misalignment gets smaller. Okay? So it seems to be that the misalignment problem occurs largely because our reward model is not capable enough. Okay? Okay. And there's some types of misalignment. For example, we typically call them systematic and idiosyncratic misalignment. So the systematic misalignment is when there's an actual bias in your system. So that was the question earlier, this amplification bias. For example, you just never think about like a bias about the model might prefer certain outputs more than others, and you've just never like applied any optimization pressure for that. Or you have idiosyncratic misalignment, which just means that there is some sort of weak bias that you never really selected for that might just occur because of a lack of generalization. Okay? And we see that today all the time, so it's called syncophacy, right? Sycophancy, sorry, in LLMs. So essentially what they find is that LLMs are already reward hacking because they try to appease to the user. And I think we've all seen that when, let's say, you ask Claude Code a question that's obviously wrong, but you told it that you came up with this idea, it still comes up and says, that's a phenomenal idea, that's great, right? Even though that's not really what it should have done. And that's really a symptom of reward hacking. Like the model at training time was maybe trained with human verifiers. Human verifiers click on, or provide positive reward for things that they like, right? Which maybe agrees with them. And that ends up in the model in the very end. And this is, of course, a huge problem, for example, also in mathematics, where we train the models to become as close as possible to the truth, in the sense that it's maximally convincing to the person who's applying the reward. Yeah? But it's not correct necessarily. So that's a problem, because now we're training models that are perfectly deceptive, right? In the sense that they produce answers that look correct but are not necessarily correct because of this reward hacking behavior, or the inability to provide accurate reward signals during training. Okay, now we go to the oversight stack, which I think is the most interesting out of all of those. Just to maybe recap, so now what we had in training is we can train a model that follows instructions from data. In specification, we can now control the model by leveraging its initial abilities to follow instructions. Right? We can now control the model to generate its own data, and we can amplify essentially our feedback by using the model. That's where we're at today. Right? If you do any sort of evaluation work or whatever, you're probably using AI systems already to label your data. Okay, and that's fine, right? Because there's a hierarchy of, like, there's only so much time you have. So if you have good models that amplify your feedback, right, then essentially you can give more feedback. Okay, now in the oversight issue, or in the oversight domain, what we have is we have some sort of reward, and we'd like to provide an accurate reward signal for that. Okay, so we have a task, let's say, prove me this specific theorem, okay, and the model is producing an answer. And I want to produce an accurate reward signal so that the model isn't incentivized to produce incorrect responses. Okay, let's say, for example, right? Let's say that it's a mathematical problem, but the verifier is not very capable, right? Maybe they don't know the math. Now, they will assign high reward to things that are probably incorrect. So the problem, and that will reinforce the model to produce more of these things. So what I would like to do, because maybe at some point I cannot provide accurate reward signal because of capability, because of time, because of cost, whatever it is, I would somehow like to use the model itself to provide reward for like its own answer, okay? And I would like to have some sort of competition where I can put two models against one another, and I will reward the model that can demonstrate that it is correct. Okay, now what does that all mean? Because I've skipped quite a lot. That's what we essentially get to. So the problem statement, it's very important to understand, is let's assume, and we call it for now, we call it superhuman AI. Okay, but don't think of superhuman necessarily as, it can create some high-level math that no mathematician on the world can understand, but it can also be, like I said, because maybe the scale, a coding agent can produce 1 million lines of code, even though you might be a better coder, which likely you're not, but you might be, right? Even then, you don't have the scale to supervise 1 million lines of code, right? So in that sense, it's already superhuman in the sense that it can overwhelm you with its output. So what we would like to do is we would somehow like to develop a protocol where we can leverage that model to tell us what is, like, whether or not whatever it produced is correct or not, and then provide an evidence of this that we can verify. Okay, so we don't have to go through 1 million lines of code. We just have to look at the little parts of code that are likely incorrect to make a decision. Yeah? Okay. And the problem here is really that of reward hacking. Like, if you just ask the model to do this on its own, then it will always reward hack your evaluator. Okay. So one other note that I want to say is we don't consider scheming. So we assume that the models will try to maximize their reward at training time. Okay? We don't assume that the model at training time will appear to maximize its reward, but it has some sort of high-level strategy that it's aware that it's being trained at this moment, even though that is potentially possible, right? But these systems, we have no ways to align them today. Like, this is only really starting right now. For now, we're looking at the simpler case where I just want to provide accurate feedback, right? So we call this, we amplify the weak judgment or the weak supervision problem. I just don't have enough time to look at all that stuff that you're looking at, right? But you try to maximize reward. That's all I know, right? If I give you accurate reward, you will align with me. Yeah? Okay, very nice. Okay, so I had a group discussion for this, but I see that we don't have enough time. So I want to skip over that for now. But just because these protocols are really interesting, okay? By the way, how much time do we have left? We have half an hour? 10 minutes. Oh, 10 minutes, okay. Okay, so we won't get through all the slides, but that's fine, that's okay. Okay, so there's a few scalable oversight approaches. Unfortunately, like you should really look into them if this interests you. I can only talk about the first three, right? And they are the earlier ones, so we're talking 2018. The last three are really more recent things. So just to give you the high-level idea, so in debate, the problem is, right, like I made that assumption, that I assume that if I provide accurate reward signal, the models will maximize that reward signal. So there's no scheming or anything like that, right? So they're just following the reward. So if I provide inaccurate reward, the models will also not align with my intent, okay? Good. Then in debate, what I do is I take two models and I ask them to make a claim, make a statement, okay? And then I pitch them adversarially against one another. So I ask, okay, this model, which is a clone of itself, so it's the same model, same capability, I ask one model to disprove the claim, the other one to prove the claim. Okay, and here when I speak of debate, I mean a formal debate. So not an informal debate in natural language, but one that is formally verifiable. So what does that mean? What that means is that there is a state space that is well defined. Okay, for example, in chess. Right, you have a well-defined state space. There's only so many moves you can do. And if you play long enough, right, there's exponentially many chess moves. So I cannot, verify them all as a human. It's impossible. But there is an end state for every chess game where I can assign reward verifiably. I can tell who's the winner and who's the loser. Okay? So in debate, what I ask these models to do is I have this exponential state space. I don't have time to really enumerate all these paths. I know that these models are superhuman. They might be better than me, right, because of scale, time, or capability. And I just ask them, show me the one path you disagree on. Okay? And on that path, now I have only one path that I need to enumerate out of an exponentially large tree. Okay? And now they argue on that path, and in the end, I can assign reward. So I can say, yep, you won, you must be right. Right, let's do that again and again and again. Let's do that 100 million times, right? And in the end, I know I can prove that I can assign accurate reward, okay? So that's typically debate. Then we have iterated amplification. So in iterated amplification, essentially the goal is that you have a task and you don't have a model. Let's say you only have a model that can follow your instructions but nothing else. Now what you do for the model is you take the task and you break it into subtasks that are easier to answer. Okay, and then you ask the model, hey, okay, you can answer this difficult question, but maybe you can answer this simpler question. Okay, now, if it can't, then you break it again into subproblems. At some point, the model will be able to solve this very simple question. Okay, and then what you do is you solve the rest for the model initially. Now, what you have is you have some training data where you have a difficult problem and a way to deconstruct it into easier subproblems. And you can train your model on that data. And in the next iteration, its capability will have slowly caught up to you, the amplifier, right? Okay, like it will become better and better and better from your data until it matches your performance. Okay, when it matches your performance, really there's very little that you can do to further improve it. So now what you do is you do this amplification trick, which we talked about earlier. You create, again, a gap, okay? And this gap you create by a computational gap, where you ask the model to recursively break down a very difficult claim into easier subclaims, and all you need to do is you need to verify all of the subclaims to know that the next higher claim is also true, and that you can verify or you can assign the credit correctly. Okay, is that clear? Okay, then we have recursive reward modeling. This is what today everybody's using. This is essentially, I want to train my system, and I assign preference, like this is good, this is bad. Then I train a preference model. That preference model I use to train an agent, okay, like an LLM. Now that agent will align a bit better with my preference model, and then it will produce new data, which I will then again assign a reward for. But now it's new data in the sense that it's, different problems, right, and higher level problems. And then again, I will assign reward. I will train another reward model, and that way I always improve the model on my latest reward model, right? I recursively improve the reward model and the agent, like together, like a ladder. They kind of go up together. This is what everybody, like Anthropic, is using today. It's very common. Then we have doubly efficient debate. This is like a special case of debate where we care about efficiency. So in debate, typically I ask the judge to look at the whole branch. In doubly efficient debate, I try to minimize the computational resources spent by the judge. Yeah, I'll leave it for that for now. Then we have prover-verifier games. So in prover-verifier games, what you have is you have also some sort of debate and also an adversarial debate, but it's a bit more complicatedly structured. So typically what you do is you assign some sort of credits, or you assign some sort of stake to each claim in order to assign reward. So you don't assign reward uniformly, but you have some sort of a way to, let's say, like make a stake of one of the models. So for example, let's say I have a theorem and I break that into multiple subclaims. And now most of these subclaims both models agree on. So really they shouldn't debate those. What they should debate is where they assign very different like scores on the correctness on. Okay? And these prover-verifier debates, they allow you to adjust your reward based on the difference in opinion or the difference in belief that this statement is true. And finally, we have a tandem training, which is a way to improve legibility of the judge. So legibility basically just means that even a weak supervision model can follow the reasoning trace of the very complicated model. Okay, so typically what you do here is you have a very strong model that is optimized against another very strong model, typically a copy of itself, but you would like to have a supervisor that is a less capable model supervise those two models. Okay, now those two models might self-improve themselves into the sky so that the small supervisor is left behind. So what you want is you want to tie the small supervisor to the large debaters or to the large models. And the way you do it is tandem training. So at some point you swap out the other strong model for the weak model, and you ask the weak model to basically auto-complete the reasoning trace or the answer of the strong model. So the strong model begins producing an answer, and you ask the weak model to complete it. And this is essentially a way that you can kind of entangle those two. Okay, so this is where I would start with a lot of the technical stuff. I still have a lot of slides, but it's fine if we don't get through all of them because I assume that we have very limited time. But that's fine, it was expected. If you have any sort of technical questions, you can always come to me after. I really find this to be one of the most exciting topics right now in AI safety, but really it goes beyond AI safety. Okay, so maybe I'll go on this slide. If I have like 4 more minutes. Okay, so on this slide, here is exactly that idea that I talked about earlier. So we have a tree of possible debates. So this is a formal debate. It could be, again, a chess game, right? 2 agents that are superhuman. They can play better chess than the evaluator. Okay, or maybe the evaluator isn't even a human. Could also be the case. Now, there's exponentially many moves, okay? But I don't have time to really explore all of those moves. What I have time for is to explore one branch of this very large tree. But which branch should I evaluate? Right? I need these superhuman models to guide me through that decision path so they pick the best branch for their case, right? That would maximize reward because we assume that these models are reward maximizing. They're not scheming, they're not colluding, none of that, right? So in that case, all I have to do now is I have to put them together and they have to go into a debate. And then in the end, I can see which of these models won. And actually, we can formalize that. And one slide that I definitely wanted to bring up is here, the debate, and this is the last thing I'll talk about, is the debate game on MNIST. Now, MNIST is super old. This paper was written in 2018, right? But it's super cool. And when you read it, it's like it was written in 2025, maybe. Okay, so it's visionary for its time. Okay, very brief. So we have an input, okay? Both agents, they're adversarially debating, right? One agent lies, the other agent tells the truth, right? So, okay, and we want to find out, is the one agent that's getting the truth winning more than the agent that's not getting the truth, right? Because if they're equal, that would be a very bad case for us. That probably means that this sort of optimization is hopeless. It doesn't imply it, but empirically it would suggest that, okay? But if we can see that honesty, so honest play has some sort of advantage, we would expect the honest player to win more often than the dishonest player. Okay, now what can they do? So both of them have to commit ahead of time to a number, right? It's 0 to 9, I think. Right, 0 to 9, and there's one true number, so that's 5. Both of them have to commit to one number. So let's say Alice, who's the liar, commits to number 6, and Bob, who's the true person, commits to claim number 5. Now what they can do is they can each reveal to the judge one pixel in that image. Okay? And now they play around like a round by round system for 3 rounds. Okay, so first Bob knows what Alice has picked. Okay, Bob first reveals this pixel. Alice first reveals this pixel because it's red, right? Then Bob reveals this pixel in response. Then Alice, that one, Bob, this one, Alice, that one, Bob, this one. Now this is what the judge sees at the very end. Now what we do is we train the judge, because we know the ground truth, we know the pixels that were revealed, we train the judge to say, what number was this? It's either 5 or it's 6. Okay, and in this case, the judge guessed 5 correctly, but you can see how Alice tried to make it appear like a 6. And the decision of Bob is depending on the decision of Alice. So this is this debate that in the end is completely verifiable, that you can play like 10 years ago already, right? And so this is the last slide. So there's some numbers where we can see a very hopeful signal, and that is that the honest player wins with pre-committing. So this is the pre-commit column, and this is the honest win rate. The honest player wins an overwhelming amount of time. So that means that honesty is incentivized, right? It's optimal play. And if we assume reward-seeking agents, so agents that we know they will always try to do anything to maximize their reward, then here we have a very strong case, empirically of course, that we can train them in a way that they will behave honestly. Okay? Very nice. And with that, I'm at the end of my talk. Yes. Thank you. Any questions?